In this video, I'm going to be building a binary adder, specifically a 4-bit binary adder. So first of all, if you don't know how the binary number system works, you can check out my previous video on it, which I'll link to in the description. As if you don't know how binary works, this video will be a lot harder to understand. So first of all, to be able to build a binary adder, we need to understand how adding in binary works. So in binary, starting off with just one single bit, if we have 0 plus 0 in binary, that will equal 0. And if we have 1 plus 0, that will equal 1. If we have 0 plus 1, that will equal 1. And finally, if we have 1 plus 1, that equals 0. And then we also have a carry of 1. So, for example, in decimal, if we're adding, say, 5 plus 6, that equals 11, or 1, carry 1. So this carry will be necessary when we're adding more than 1-bit numbers, as we'll need to carry this and add it to the next place. So, for this circuit, we will have two inputs, our A and our B, which are the two numbers we're adding together. And we will also have two outputs, just our sum, as well as our carry bit, which I talked about earlier. So, to split this up, we have, first of all, for our sum, if the A input is 0 and the B input is 0, our sum is 0 because 0 plus 0 is 0. And if our A input is 0 and our B input is 1, our sum is 1. And if our A input is 1 and our B input is 0, our sum will be 1. But if our A input is 1 and our B input is 1, our sum will be 0 because in binary 1 plus 1 is 2, and 2 gets carried into the next place, so our sum is just 0. Now, if you've watched my previous basic logic gate video, you will know that this table here is the same as the table for the XOR or exclusive OR gate. So to get the sum from our two inputs, we just need a XOR gate. Now, for our carry, we have our A and our B inputs. If these are both 0, our carry will be 0. If one of them is 1, our carry will be 0. But, like I said with this one, if both of our inputs are 1, our carry will be 1. And again, if you watch my basic logic gates video, you will know that this is the same table as the AND gate. The output is only 1 if both of the inputs are 1. So to make this circuit, we'll have our A input and our B input, and we just need to feed these into an XOR gate and an AND gate. So we can feed our A input into each of them and our B input into each of the gates. And then we have our XOR gate here. The output of that will be our sum, and the output of our AND gate here will be the carry. So this circuit here is also known as a half adder. And to simplify this, we can draw this as just a box with our two inputs and our two outputs. And now, from now on, we're going to think of this here as our carry out, or I'll just write it as CO. We'll abbreviate sum as S, and A as A, and B as B. Now, the reason this is called a half adder is because since we have a carry out, we also need to have a carry in. So essentially, if we do have a carry from the previous place, we need to add it to the A and B. So essentially, we're adding 3 binary numbers instead of just 2. But first of all, I will show you a half adder working on this breadboard. So here I've built the circuit the same as I drew it out on the paper. And we have 2 chips here, the 74LS86, which is a quad XOR gate, so it has 4 XOR gates on this chip, as well as a 74LS08, which is a quad AND gate, so there are 4 AND gates on this chip. And I'm just using one of each of the gates, and you can see I have the A and B inputs here, which are connected up to the inputs of the AND gate and the XOR gate, and then I have the outputs of each of the gates connected up to these LEDs. So this is the carry bit, this red LED here, and this is the sum bit, the green LED. And you can see I have these 2 switches for the A and B inputs with ground and power. And I've also connected these chips up to power and ground. So if we test this out, we can see right now both of these inputs are zeros, so the sum and the carry are both zeros. And if we set one input to a 1, we can see the sum is a 1, or the other one. But if we set both inputs to 1s, the sum becomes 0 and the carry is 1, just like we saw from our paper. Next up, what we're going to build is a full adder. So that will have our A input, our B input, as well as a carry in input, and the same outputs as we have here. So to build this, we're going to start out with a half adder here. And this box, of course, just represents our other circuit we drew over here. And we will just have our A and B inputs into here. And we will also need a second half adder. Now, like I was saying, essentially what we want to do here is add 3 binary numbers together. So we can just take the sum of this half adder and feed it into one of the inputs of the second half adder. So what we're doing is we're taking the output of this half adder here and feeding it into the input of the second one. And then our other input here can be the C or carry in input. So we're adding all 3 of these together. And then on this half adder, our sum here will be our sum. And then to get the carry out of the full adder, we are going to use an OR gate. So we'll feed each of these into an OR gate, and this will be our carry out. And how this works is if either of these have the carry out set, we want the carry out to be set here, because that means that at least 2 of these are on. Now you might think that we would need another half adder for this in case both of these were on, but we don't, because there's no way that both of our carry out bits from each of these half adders can be on. So what we've drawn here is a full adder, which we can draw in a box here with our 3 inputs as well as our 2 outputs. So now I will show you this working on our breadboard. So here I have the circuit on our breadboard. And I have the 74LS86 and 74LS08 like I had on the half adder. To construct two half adders, we have one up here and one down here. And I also have the 74LS32, which is a quad OR gate. So there are 4 OR gates on this chip. And how this circuit is put together, like I showed on the paper, is we have our A input and our B input. These are going to the inputs of this top half adder here. And then from this half adder, our sum is feeding into one of the inputs of the second half adder along with the carry in bit here. And our carry from both of the half adders are feeding into the OR gate here, and the output of that goes to the carry out bit here of the full adder. And of course the sum from our second half adder feeds to our sum here of the full adder. So to demonstrate this working, if we have any one of our inputs on, our sum is on. If we have any 2 on, just our carry out there turns on. And if we have all 3 on, both our carry out and our sum are on, as 1 plus 1 plus 1 in binary equals 1, 1. So there is our full adder. Now, going from a 1 full adder to a 4-bit adder is actually pretty simple. All we need to do is take 4 of these full adders that we built and connect them up. So in each of these, we have our A, B, and carry in inputs, as well as our sum and carry out outputs. Now, to string these together, all we have to do is connect up the carry outs from the previous full adder to the carry in of the next adder. And then the first carry in up here will be the carry in of our circuit. And the last carry out here will be the carry out of our circuit. So you could use these to hook this 4-bit adder up to be an 8-bit adder or a 16-bit adder or so on. And then these 4 bits here will be our sum bits. And these can be labeled as sum 0, sum 1, sum 2, and sum 3. And our A and B inputs over here can be labeled as A0, A1, A2, and A3, as well as B0, B1, B2, and B3. So here we have our full adder. Now, one good thing to remember here is that our first full adder here is the lowest bit of our circuit. So this is going to be the 1's place. This will be the 2's place, this will be the 4th place, and this will be the 8th place. So if we take our built circuit here, I can show you how it works. Now, up here, I just have 4 full adders, the same as I showed you in the full adder circuit, and I'm not going to show you how they're all connected up as there are a lot of connections. But you can see with our inputs and outputs here, we have our 4A inputs, our 4B inputs, as well as our carry in, and our 4 sum outputs, as well as our carry out. So I'm not going to show you all of the combinations here because that would take forever, but I'll show you a few. So we can take, let's say, 1, 0, 1, 1 in binary and add that to 1, 0, 1. Now, to check if this works, I'm going to do the math on paper here. So we have 1, 0, 1, 1 in binary plus 1, 0, 1, 0. So we're going to have a 1, a 0, carry 1, a 1, and a 0, carry 1, or 1, 0, 1, 0, 1. And we need to remember that this is, of course, the carry out bit. So you can see on our LEDs here, we have a 1 on the carry out, and then 0, 1, 0, 1 on the sum outputs. Now you can see over here, if I turn the carry in input on, that will add one more, which puts this LED from a 1 to a 2's place. And if we go for one more example, we can turn all of these off. So for this problem, we'll have a 0, 1, 1, 1 plus 1, 1, 0, 0. And then we will also turn the carry in bit on, so that is plus another 1. So we will have a 0, carry 1, 0, carry 1, 1, carry 1, and 0, carry 1. So we can see we have our carry out bit set, as we do on our LED, as well as a 1 in the 4's place here, which we have showing on the circuit here. So, as you can see, a adder can be pretty easily constructed using basic logic gates, and this adder will be very useful in building a functional computer later on in this series. That's all for this video.